Section 15.3, double integrals in polar coordinates. The region given by r equals all the r thetas such that a is less than or equal to r is less than or equal to b, so r is between a and b, theta is between alpha and beta for constant values a, b, alpha, and beta, is called a polar rectangle, as shown in this figure. So this should be pretty similar to our definition of a rectangle in rectangular coordinates, where we have the sides of the rectangle bounded by variables set equal to certain constants, except that in this case, when r is equal to a constant, it doesn't quite give you a straight line, it gives you an arc of a circle. So it looks slightly different, but that's okay. Using the definition of a polar rectangle, we can change two polar coordinates in a double integral. If f is continuous on a polar rectangle r, given by where r is between a and b and theta is between alpha and beta, where if you take beta minus alpha, then that's between 0 and 2 pi, so we don't want to be too wide for our angle. Then we have the double integral over r of fxy dA, so our classic rectangular double integral over rectangle, equal to the iterated integral, where first we integrate with respect to r, and then we integrate with respect to theta. So to prove this, how about we consider the center of the polar subrectangle rij. So what we'll do is we'll take our polar rectangle and we'll chop it up into tons of little polar subrectangles. And then we'll look at each of those little subrectangles. We'll look at the ijth subrectangle, and we'll look at the center. And we'll say that the center has coordinates ri star, theta j star. So notice ri star is the center, so it's going to be halfway between two consecutive radii. So we could say that the ri star coordinate is equal to half of ri minus 1 plus ri, because it's the average of the two consecutive radii. And similarly for theta j is in between two consecutive theta rays, so it's the average of those two. So then, since the area of a circle with radius r and central angle theta is half r squared theta, the area of the subrectangle rij is delta ai, which will be half ri squared theta minus half ri squared theta, because this first value represents all of the area from, well, let's see, here's ri. So you could think of it as this entire area all the way over here. So that's this guy. But then you want only the area for the subrectangle. So what you'd have to do is you have to cut out all of the area over here that comes before, so that the only area you have left is this area. So the area you cut out is the area for the previous radius. So that's this value over here. Notice we're using delta theta because we're thinking of the kind of angle between these rays as this tiny change in theta. Oh, I can't even erase that anymore. Oh well. So that means that this over here, this width, is the delta theta. You can see it over here maybe also, tiny change in theta. Okay, so then notice we have r squared, we have a half. So what we could do is we could factor out the half and get this, but then we can factor, because we got two squares, we have a difference of squares. So that's ri plus ri minus 1 and ri minus 1. But half of ri plus ri minus 1 is ri star. And ri minus 1 is just the change in r, delta r. So this becomes Ri star delta r delta theta. So that means that we can rewrite our integral. Our double integral is going to be equal to the limit of the double Riemann sum, where, remember, in polar coordinates, x is r cosine theta. So in that case, it's going to be Ri star cosine theta star j, because we put the stars because we're looking at the sample point inside of our center of our polar subrectangle. And for y, remember, that's r sine theta. And then dA becomes delta AI for the particular subrectangle we're looking at. So when we take the limit of this double Riemann sum, our sample points, it doesn't matter where we take them, they disappear and just become our cosine theta and our sine theta. And then our delta AI was what we really did the work for to calculate. That would be Ri star delta r delta theta. So the Ri star just becomes an r, the delta r becomes dr, and the delta theta becomes d theta. So notice that the major thing here is that you don't just convert x and y into r cosine theta and r sine theta, but you also have to convert the dA. And in that process, you end up with an extra r. So remember, it's r dr d theta whenever you integrate with polar coordinates. And of course, you have to change your limits of integration too to make sure that they work for the polar coordinates you're looking at. So let's do an example. How about we evaluate the double integral over r of 3x plus 4y squared dA, where r is the region in the upper half plane bounded by the circles x squared plus y squared is 1 and x squared plus y squared is 4. So we'll have to draw our region r. So here's x and y, and let's put in, let's see, x squared plus y squared is 1, so that's this circle of radius 1, but it's in the upper half plane, so it's a semicircle. And let's put in the circle of radius 2, that's when x squared plus y squared is 4. Okay, and we will label this r. That's all of this over here in between these two guys. And the bottom, remember, is x squared plus y squared equals 1. And my top one is x squared plus y squared equals 4. And I can describe this region, R, as the set of points, x, y. I should probably call these points such that y is greater than or equal to 0. And it looks like x squared plus y squared is less than or equal to 4. Which is not the most convenient way of integrating by any stretch. We'd have to start chopping stuff up, because in order to solve for functions of x or functions of y, we have to get rid of these squares, which is annoying. But notice that in polar coordinates, it's super nice. In polar coordinates, I could say that this region R is the set of points r theta, such that, well, it looks like r goes out over here, starts over here at 1, and then keeps going, and ends up over here at 2. So the radius goes between 1 and 2, and it looks like theta opens up from 0 to 180. So I could say 0 to pi for theta. Way better. We can plug that into the integral pretty easily. In general, when you're looking at the region you're integrating over, whether it's r or d or whatever it is, if it's kind of like circular, or it's something that is more easily expressed in terms of polar coordinates, like almost obviously whenever you have a circle it is, then just go to polar coordinates and forget about rectangular for now. So we have our double integral over r of 3x plus 4y squared dA. Remember, we're not looking for the area over here. We're looking for the volume underneath this function that's floating above this area over here somewhere in 3D. We're just not drawing that. So this guy is not what determines when you convert to polar coordinates. It's the boundary of the region that determines if you want to convert to polar coordinates. So we always have theta on the outside because we always have to deal with our RdR term, and because we always express r as a function of theta, we never express theta as a function of r. So on the outside I'll have my integral from 0 to pi because it's my theta, and then on the inside I'll go from 1 to 2 because I'm going to do that first. And then 3x becomes 3r cosine theta because x is r cosine theta. And then 4y squared becomes 4r squared sine squared because y is r sine theta. And I can't forget my r dr d theta. Okay, let's see. So now we've got the integral from 0 to pi of the integral from 1 to 2 of 3r squared cosine plus 4r cubed sine squared. Just incorporate my extra r in there, dr d theta. And that's going to be equal to the integral from 0 to pi of r cubed cosine theta plus r to the 4th sine squared, just by taking my first antiderivative. And that's evaluated from r equals 1 to r equals 2. Notice that sine squared theta is a constant, so we didn't have to worry about that. Same thing with cosine. We just had to worry about the 4r cubed and the 3r squared. Okay, so now we plug in 1 and 2, and we get the integral from 0 to pi of 7 cosine theta plus 15 sine squared d theta. And now theta is a variable, so we have to worry about it. So in order to try to evaluate this, we need to try to integrate sine squared. So remember from section, I think 7.2, we did trig integrals, and we said that one of the easiest ways to integrate sine squared or cosine squared is to use the half angle identity. So I'm going to pull out 1/2 1 minus cosine 2 theta and use that to replace sine squared. It's half 1 minus cosine 2 theta sine squared. And I just have to do this antiderivative now. It's much easier to integrate cosine 2 theta than sine squared. This is a very quick mental u substitution. So first we get 7 sine theta for the 7 cosine. Remember taking the derivative, that's easy. And then we get 15 theta over 2, because this distributes to the 1 and distributes over there, and then the constant just gets a theta thrown in. And then minus 15 over 4 sine 2 theta. Because antiderivative of cosine is sine, but then we've got the 2, so quick mental substitution, just throw in a half so that when you take the derivative, the 2 would cancel. Okay, and we have to evaluate this from 0 to pi, which is 15 pi over 2. How about the volume of the solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared? Okay, well, the paraboloid is basically just an upside down paraboloid where we have x squared plus y squared, except it's moved up 1. So how about I just try drawing that? Let's see. Maybe something sort of like this. And then I want like this kind of circular base. So it's supposed to be in 3D, so maybe I'll put some lines over here like this. And then I can put my z-axis. And I can put my y-axis. And my x Okay, that's roughly what it's supposed to be. Notice that it starts at 1, so over here is 0, 0, 1. And here's the origin. And how about I call this circular base D? It's supposed to be a circle over here. Just not very good at drawing it. So it's kind of like this upturned bowl. Okay, well, in order to try to get a description for that circular base, how about we set z equal to 0, because then we're in the xy plane. And when z is 0, that tells us that x squared plus y squared is equal to 1. Just put 0 over there. And that's just a circle of radius 1, so that means that our region D can be described using polar coordinates pretty easily as all of the r and thetas, such that r goes between 0 and 1, and theta this time goes all the way up to 2 pi because we get the entire circle. So that means that our volume is the double integral over D of 1 minus x squared minus y squared dA. And that's just going to be the iterated integral from 0 to 2 pi of 0 to 1. Remember, theta always on the outside of 1. And then this is x squared plus y squared being subtracted from 1. So that's just r squared. And we can't forget our r dr d theta. So this is the integral from 0 to 2 pi of, oh, notice there's no thetas. Wonderful. So we can just put d theta. And we can split that from the integral from 0 to 1 of r minus r cubed dr. Remember that when we do an integral of a product of functions of separate independent variables, in this case we just have one function of r and then a function of theta, which is basically just 1. So we could separate that very easily and then separate our integrals. We'll do that pretty often for polar coordinates. So now we integrate each of those. We get 2 pi for this guy, just 2 pi minus 0. And for the other integral, we get r squared over 2 minus r to the 4th over 4, evaluated from 0 to 1, which is pi over 2. So that's our volume. Notice they didn't even really give us d, we had to figure it out, but they gave us the solid bounded by the plane z equals 0. So we were able to just basically project downwards and figure out what it would be. Notice that if you were to try and use rectangular coordinates to compute this volume, you would have to say that the volume v is equal to the double integral over d of 1 minus x squared minus y squared dA, and convert that using Fubini into the integral from minus 1 to 1 for x, and then for y you'd have to go from minus the square root of 1 minus x squared to the square root of 1 minus x squared of 1 minus x squared minus y squared dy dx, which is super difficult to evaluate. You'll end up having to evaluate the integral of 1 minus x squared to the 3/2 power, which is just horrible. So you may not love polar coordinates, but you should definitely work them into your repertoire. Same as before, if we have some functions of our independent variable bounding our curve, then we can just integrate by throwing those functions into the limits. This is when we did type 1 and type 2 regions. However, in polar coordinates, we only have one type of region because we don't express theta as a function of r, but we do sometimes express r as a function of theta. So that just makes it so that we can have some interesting stuff going on along the boundaries from the origin. But on the sides, it's still going to stay straight. Okay, so it's not that bad. We can do an example by using a double integral to find the area enclosed by one loop of our four-leaf rows, r equals cosine 2 theta. So we've graphed this in the past when we did polar coordinates. It's just basically a four-leaf clover. So let's see if I can draw it. The answer is probably no. And something like this. and it's supposed to be completely symmetrical. And I only want the area of one loop. So I want the area of, let's say, this one. And that's when theta goes from this ray at minus pi over 4 all the way to this ray at theta equals pi over 4. So that means that we can describe our region D as the set of points r theta such that theta goes from minus pi over 4 to pi over 4. Those are my constant limits. And then we have to be a little bit more careful about r, because r is not just one consistent distance away from the origin. In this case, it varies depending on where we are in our function. So r goes from 0 to whatever the r value is, in this case cosine 2 theta. So I should put that r is between 0 and cosine 2 theta. Okay, so now I want the area of D. So the area is just the double integral of 1, remember? Same as it was in rectangular, except that we'll convert from rectangular to polar. So we'll do the integral from minus pi over 4 to pi over 4 for theta, and then on the inside from 0 to cosine 2 theta for r of 1 times dA, so dA becomes r dr d theta. So then that becomes the integral from minus pi over 4 to pi over 4 of half r squared from 0 to cosine 2 theta d theta, which is just half times the integral from minus pi over 4 to pi over 4 of cosine squared 2 theta d theta when you plug in 0 and cosine 2 theta. So I need to integrate cosine squared. I'll use my half angle identity again. So I'll make cosine squared is half of 1 plus cosine 2 theta. So I'll end up with a fourth. And then I was starting with 2 theta. Since it's cosine squared is half of 1 plus cosine 2 theta, and I already have a 2, so it should be 4 theta. So I'll integrate from minus pi over 4 to pi over 4 of 1 plus cosine 4 theta. And then you can think, okay, yeah, this does work as a half angle identity, because when I go backwards, I do get half my angle. And this is just 1/4 theta plus 1/4 sine 4 theta when we do our antiderivative, evaluated from minus pi over 4 to pi over 4. And doing the math, we just get pi over 8. Let's try finding the volume now of the solid that lies under the paraboloid c equals x squared plus y squared, above the xy plane, and inside the cylinder x squared plus y squared equals 2x. So how about we try drawing the region we're integrating over, and we'll also try drawing our solid so that we can actually try to see what this looks like. Well, the region is a cylinder, specifically a circular cylinder, so I just have to draw a circle in the xy plane. That's basically the shadow of this thing. Wow, pretty bad circle. Let's see if I can get a little bit better than that. Okay, so this is the circle x squared plus y squared equals 2x, because what you do is you complete the square. You subtract 2x, and then you add half of 2 is 1 to both sides, and you end up with x minus 1 squared plus y squared equals 1 when you factor it. So that means that the center is at 1, it's just moved over, and the radius is 1. And we can just call this our region D. So how about we also draw what this looks like in 3D? Because in 3D we've got a paraboloid and a cylinder. So how about I try drawing the little top of my cylinder. Try it again. If at first you don't succeed. And I'll try drawing now my paraboloid cutting through this guy. Let's see. Something maybe like this. It was going good until, okay. And let's see, it should wrap around. Tricky drawing 3D. Okay, and then I should complete my cylinder. So something sort of like this. So here's my z-axis, here's my y-axis, and let's say here's my x-axis. Okay, so it looks like we want the volume of solid under the paraboloid and inside the cylinder. So it's underneath the paraboloid, so it's this part, but it stays inside the cylinder. I'm going to shade it like this. So this is the volume we want, which makes sense that it would be a circle in the xy plane because the base of the cylinder is a circle in the xy plane. Okay, so now that we have a better, clear picture, how about we try to use polar coordinates to do this because we've got a circle. So remember that x squared plus y squared is 2x. That's what we were originally given before we completed the square. And that means that in polar coordinates, x squared plus y squared is r squared. X is r cosine theta, so r squared is 2r cosine theta. So taking square roots, we get that r is 2 cosine theta. So our region D can be described as the set of points r theta such that theta goes from minus pi over 2 to pi over 2, and r goes from 0 to 2 cosine theta. And that means that our volume is the double integral over d of x squared plus y squared dA, and that's equal to the integral from minus pi over 2 to pi over 2 of the integral from 0 to 2 cosine theta of, well, x squared plus y squared is just r squared, and then we have our r d theta. So that's equal to the integral from minus pi over 2 to pi over 2 of r to the 4th over 4 from 0 to 2 cosine theta d theta, which is 4 times the integral from minus pi over 2 to pi over 2 of cosine to the 4th theta d theta. And, well, I'm going from minus pi over 2 to pi over 2, and cosine 4 theta is even. So how about I just split this into half? I'll go from 0 to pi over 2 and double it. So I'll get 8 times the integral from 0 to pi over 2 by symmetry of cosine to the 4th theta d theta. Okay, and that's going to be, well, cosine to the 4th is just cosine squared squared. Remember, cosine squared has that half angle identity, half 1 plus cosine 2 theta, so I just have to square that. So I get 8 times the integral from 0 to pi over 2 of 1 plus cosine 2 theta over 2. I have to make sure the half is on the inside because it has to be squared. Okay, so if we square our half, then the 2 inside becomes a 4, and then we have 1/4 times 8 is 2. So we have 2 times the integral from 0 to pi over 2 of 1 plus 2 cosine 2 theta plus 1/2 1 plus cosine 4 theta, because we just FOIL what's left, and integrating that's pretty easy. We get 2 times 3 over 2 theta plus sine of 2 theta. Quick mental substitution over here to get rid of the 2, and then 1/8 sine 4 theta. And we evaluate that from 0 to pi over 2. So that just becomes 2 times 3 over 2 times pi over 2, which is 3 pi over 2. So that's our volume.